Okay, here's another look at calculating work and net work. Oops, this should actually be negative and net work part 2. And this should be video 7.1 C. Now we can start. So we've got a block going down in your favorite situation, an inclined plane, tilted at an angle of 30 degrees to the horizontal. So theta here is 30 degrees. Okay? It's going to slide 2 meters down the hill. Okay? And the force of kinetic friction is 5.3 newtons. Theta, again, 30 degrees. What forces are acting? Let's enumerate them. Well, one of them is always weight, gravity, right? Which is always easy. It's always straight down this way toward the center of the earth, mg. And I want you to remember the angle between it and the negative y-axis. That is theta. Okay, so that's 30 degrees. Okay. What other forces are acting on the block? The weight's straight down. Okay. I think I'm going to move this displacement vector. I think it might be better if I took this. It'd be more informative, it'd be more instructional to move it down here like this. Okay, like that. In the positive x direction. Okay, so what other forces besides the weight, right? Displacement's not a force, that's just the displacement. That's this arrow that goes from where it started to where it stopped. But now, so the first force, let's list our forces here. mg is one of them, that is the weight. What's another force acting on the block? The normal force, right? What direction is it? Well, what does normal mean? It means perpendicular to the surface of contact. So the normal force is in the positive y direction. Right there. So we got weight, we have the normal force, and finally we have, it's given to you, the static frictional force. The kinetic frictional force. And the force of kinetic friction, what direction is it in? Not static now, kinetic. What direction is the kinetic friction always in? It always opposes the motion. You can think of it, it opposes the displacement. It's just downhill. So the static frictional force is uphill in the negative x direction. So the kinetic frictional force points uphill. So we have 3 forces acting on it. The kinetic frictional force pointing uphill, opposed to the direction of motion. We have the normal force pointing in a direction perpendicular to the direction of motion. And we have the weight straight down. Okay, those 3 orange forces, did they come off as orange? I think they come off as yellowish orange, yeah. mg, n, and f sub k. And now what I want to know is what is the work done by each one of them and what is the total work done as the block moves 2 meters down the hill. Okay. Take them one at a time. Or someone used the green, I think. What is the work done by gravity? Well, you'll remember, I'll put our general formula down here. Work is whatever force is doing the work, the magnitude of whatever force is doing the work, times the magnitude of the displacement times the cosine of the angle between them. Now this theta and that theta are not the same theta. Please note. This theta is in the work definition, this theta here is the angle, as I've already said, angle between F and D. So we can't just put in 30 degrees there because that's not the same theta as that one. Okay, these two thetas are the same. We've seen that before many times, 3 or 4 times at least, in examples on this very same piece of glass. Those two thetas are the same. But this is the angle between F and D and is not the same as those in general. So that's our definition of work. Let's apply it to all 3 of our forces, mg, n, and F sub k, and then find the total work done. Work done by gravity is going to be the force of gravity, mg, times the displacement, times the sine of what angle? What is the angle between the force of gravity and the displacement? Well, the force of gravity is straight down. Displacement's here. So what I'm asking is, y'all, what is this angle right there? If this is 30 and this is 30, then the blue angle has got to be 60, because when you add them up you get 90. So the angle between the weight straight down and the displacement down the hill is 60 degrees. So that's going to be mg d sine of 60. Okay. Because again, displacement's down the hill, mg's that way. That blue angle there is going to be the 90, which is, you see the right angle here. Right? That angle there is a right angle. If it's not a right angle, it's a wrong angle. That angle there is 90. So if this is 30 here, that's got to be 60. So mgd sine 60, you plug your numbers in, you know your numbers. They're given to you free of charge. So this is going to be wrong color, that's what that's going to be. That's going to be the mass, which is 2.5 times 9.81 times 2.0 times sine of 60 joules. And when you do your math, crunch your numbers, you get that that's 24.52 joules. Or if you round it, it's going to be 25. That is the work done by gravity. Okay. And the tricky part of that was the sine of 60, getting that angle 60. That's the tough thing. So review that. Okay. Now, let's find the work done by the normal force. That's going to be the normal force itself times d times the cosine. Again, it's an angle thing. What is the angle? Behold the free body diagram. What is the angle between the normal force and the displacement? In unison, 90, right? Because the normal force is up, displacement is down the hill. Okay, that's a 90-degree angle. So it's going to be nd cosine of 90. Cosine of 90, you know what that is? 0, which is great because it really makes life simple. You don't have to know what the normal force is to know that the work done by it is equal to 0. So the work done by the normal force is 0. The normal force does no work. Okay, I'm going to write something here. N does no work because it is perpendicular to the displacement. The normal force does no work because it is perpendicular to the displacement. That is true for any force that is perpendicular to the displacement in any situation. Because whenever you have cosine of 90, you're going to have 0. And that doesn't, it makes everything, when you multiply anything by 0, you still get 0. So the normal force does no work here. It's perpendicular to D. And that is true for any force in any situation that is perpendicular to D, the displacement vector. Okay? Normal force does no work. Now what's the work done by the kinetic frictional force? Same idea, right? Here we plugged in, for F, we plugged in mg. For normal force for F, we plugged in N. Here for F sub k, the frictional force, we're going to plug in F sub k. Okay? F sub k, d, and then cosine. Talk about the angle in a second. But again, we have plugged in for the force here because we're talking about the work done by the kinetic frictional force. We plugged in F there. So the force is different every time. The displacement's the same. There's only one displacement. But the forces are each different. Mg, N, F sub k. And the angles are all different because these forces act at different angles. So the angle between these forces and the displacement vector is going to be different every time. Speaking of which, what is the angle between F sub k in the negative x direction and the displacement in the positive x direction? It's 180, right? Negative x is F sub k up the hill, d down the hill. Remember, this angle is the angle between the force in question and the displacement. So here, the force in question is the static frictional force, which is uphill. Displacement is always downhill for all calculations here. So the angle is 180. And you'll remember from last time that the cosine of 180 is -1. So the work done by the static frictional force is going to be 5.3 newtons. That was given to us, the magnitude of the frictional force, times 2.0 meters times -1. Work done by the static frictional force. I keep saying static. Why do I keep saying static? If I said static like 3 times in the last minute, I meant to say kinetic every time. I don't know why I keep saying that. I got fixed on that earlier and I can't get it out of my head. The work done by the kinetic frictional force is going to be negative. 5.3 times 2 is 10.6 times -1 is minus 10.6 newtons. So that is the work done by the third force, the force of kinetic friction. And so the net work, the total work, again, I think the book uses the total subscript, is going to be 25 joules plus minus 10.6 joules. When you round for significant figures, you get 14 joules. 14 joules is the net work, the total amount of work done. You just add them all up like numbers. There's no vector stuff going on with work. Work is a scalar. You have to consider some vectors as you calculate it, but the work itself is never a scalar, always a vector. Okay, 3 forces acting at the same time through the same displacement. 3 different values of work and 1 net work. There you go.